So today we're going to start chapter 2. We're skipping over to 1. We're going right into 2.2. And 2.2 is on functions. So first thing we're going to define is what a relation is. And a relation is just a set of ordered pairs. However, a function is a special type of relation. And what a function is, it's a relation for each value of the first component of the ordered pair, so the x, is going to be exactly paired with one value of the second component, which is the y. So for each value of x, there's only one y value. So bottom line, if you get a list of ordered pairs, what we're going to look for is to check the x of the ordered pair and make sure they're all different numbers. If any number repeats, it's not a function. When you are looking at an ordered pair, the x is the domain and the y is the range. So the independent variable is your x, the dependent variable is your y. For domain, now generally when we're talking about different graphs of functions, whether it's the quadratic function, the radical function, rational functions, we would always start out by saying the domain's all real numbers, but there'll be specific cases where the domain wouldn't be all real numbers, maybe if it were the case of the square root or different ones. But always start out by thinking, oh, the domain's all real numbers, and there may be numbers that you're going to pull out of that. Now, in the graphs today, there's going to be gaps in between, and then the domain won't be all real numbers. And we're going to write that in interval notation. Now, also to determine from a graph, if it's a function, we could do the vertical line test. And what that means is we're going to draw vertical lines up and down our graph. And if it touches our graph more than once, then it's not a function. I'm going to demonstrate this. So the next slide is just stating what we would do. So if I give you a graph, we just draw vertical lines up and down. If it touches it more than once, it's not a function. So for example, here's my blank coordinate plane. Let's put some functions on here. So if I have a function that looks like this, if I draw a vertical line down, notice it's only touching my graph one time. This would be a function. Now, if my graph was like this, or to look wavy like this, and if I draw a vertical line down, notice my vertical line would cross the graph, and this particular vertical line, 4 times. So as soon as it hits it more than once, it's not a function. This one would be. Yes?
You're basically looking at each x coordinate has more than one y coordinate?
Then it's not a function.
Okay.
Yep. So each x has to be paired with exactly one y.
Okay.
All right. Now when you're given a list of ordered pairs, if they're asking you to determine if this is a function, all we need to do is look at the x of our ordered pair, and if all of the x's are different numbers, then you would say, yes, this is a function. So notice all of my x's are 1, -2, 3. They're all different. So yes, this relation is a function. However, my next example, notice that the x's repeat in the first 3 ordered pairs, so this would be not a function. You also represent a function or a relation with a mapping diagram. So go ahead and add to this picture that this first oval shape is the x's, these are the y's. Sometimes they'll have arrows indicating what the input was and what came out of it. So here, is this a function? Is each x paired with exactly one y? Yes, it is. So what we're looking for here is that there's only one arrow or one line coming out of each of the x's. Notice on the next one, notice the 2 has 2 things coming out of it, so this would not be a function. Now, also keep in mind, I could turn this mapping diagram into a list of ordered pairs. So for example, on this one, This would create the order pair 1, 2, negative 2, 4, 3, 1. Down here, it would create the order pair negative 4, 1, negative 2, 1, and negative 2, 0. So see the arrow coming out of the negative 2 is pointing to the 1 and to the 0. So that one would not be a function. Next, we're going to identify the domain and the range from either a chart, from ordered pairs, or even a mapping diagram. Remember, the domain are the x values, the range are the y values. So domain is x, range is y. So from my list of ordered pairs, when I list my domain, I'm going to list it from least to greatest, and I'm going to put it in the little braces. And I'm not going to repeat anything. So my domain here is going to be 3, 4. I've already listed the 4, so I don't need to list this one again. And then 6. And then I put it in the little braces. Then my range will be the y values. So negative 1, 2, 5, and 8. Is this a function? No. The 4 is repeated, so it's not a function. Diagram. So here we go with the mapping diagram again. This is x, this is y. So again, the domain is everything that's in that first oval. So this would be 4, 6, 7. Oh, let me put at least to greatest. Let me back it up. It doesn't really matter, but let's put at least to greatest. 4, 6, 7. Maybe possibly on a standardized test it would be least to greatest. Again, technically the order doesn't matter where you list it. And then the range would be that second oval or what's underneath the y, and that would be A, B, C. Is this a function? Yes. Good. Okay, so y's can repeat, but x's cannot. So look at the next one. Okay, notice my domain. All of the numbers underneath that x column do not repeat. However, the y's repeat, but that's okay. This is still a function. So each one of those x's could go to the same y and still be a function, but you can't repeat an x. So we're going to be given a picture of a graph, and you're going to be asked to find the domain, the range, the increasing part of the graph, the decreasing part, the constant part of the graph, and we're going to be writing all of this in interval notation. So when your graph rises from left to right, this would be increasing. When your graph goes down from left to right, this would be decreasing. And when it's a straight flat line, this would be a constant graph. Okay, and we're going to put in numbers and infinities to show where it increases, decreases, and stays constant. Yes? Now, we're eventually going to cover all of these different types of functions in their own chapter. So we're actually going to have like a chapter on quadratics, maybe a chapter on cubics. So this is actually the graph of a quadratic function. It's a parabola. You might have seen this in Algebra 1. Now, always start out by thinking that the domain is going to always be a real number. It's always all real numbers. However, there may be the situation where there may be gaps in your graph. But for this one, notice there's arrows on the end. So what this tells me that eventually this U is going to keep on going and keep getting fatter and wider and eventually cover every x value on this x-axis. So that's why the domain here is all real numbers. So from negative infinity to positive infinity. That U is just going to keep getting bigger because it's got arrows on the ends. Now, for the range though, it's not going to be all real numbers. Because which way are those arrows pointing? They're pointing upward, right? Okay. what is the lowest number on this graph for the y? 0. So my graph for the range, the lowest point it's going to have is the 0, and it's including 0, so it gets a bracket, and then that's going to infinity. That would be the range, because it starts at 0 and it goes to infinity. Everybody good on that? Yes. Because it's a solid line, so it includes 0. If it were an open circle, we would use a parentheses. Next, we're going to talk about where the graph increases, where it decreases, and where it's constant. Now, not all graphs are going to have all three. Some may have an increasing only, or a decreasing only, or maybe even a constant, or maybe a portion of all three. This one actually has an increasing part and a decreasing part, but no constant part. So again, sort of think about the line sort of like slope. So don't look at the arrows, because you might look at this and think they're both going up, they're both increasing. But again, this is just telling me my graph is going way over off the page. So again, if you think about this line in the direction it's going from left to right, it's going down. It's like a negative slope. So this side of the graph is decreasing. Left to right. So if I were walking along here and going from the left side of the graph to the right side, the first point I come to would be up here. Then the next point, if I were to walk here, it's here. Then the next one, it's a little bit lower and a little bit lower. So this side of the graph is decreasing. Once it hits the 0, that's where it's going to turn around and then start going up and start increasing. So my graph is always based off of the domain. So my graph is going to go from negative infinity for the decreasing, negative infinity, up to the 0. Now, when we write increasing, decreasing, and constant, we're always just going to use parentheses for everything, okay? Even if it started out originally as a bracket, in the increasing, decreasing, constant, only use parentheses. Now, that's the decreasing part. Once it hits 0, then it starts climbing again. So for the increasing portion, it's going to go from 0, and again, it's not a bracket, it's a parentheses, to infinity. And the constant part, it doesn't apply here. There isn't a constant in this graph. Yes?
So for like increasing and decreasing, you just put like an interval notation, like the domains.
So if it had a constant, it might do something like go down, get flat, and then go back up. That would be a constant, the flat line. All right, let's try another example. This is the graph of a cubic function. So again, the graph, if you notice the arrows on the end, eventually this is going to keep going, eventually cover the entire x-axis, and it'll keep going and eventually cover the entire y-axis. So both the domain and the range for this one are all real numbers. So I'm going to write negative infinity to positive infinity on both. And again, let's think about, notice my graph is rising from left to right, so this is increasing. And then this piece over here, it's still going up. So again, my entire graph here is increasing. No part of it is going to start to turn constant or decrease. So my graph is only increasing from negative infinity to positive infinity. The decreasing doesn't apply, same as the constant. My graph continually goes up. Don't look at the arrows and think it's pointing down. Now we're going to do one where it's broken apart. And this will be more of the type you're going to see. Okay, so again, domain is X, range is Y. So again, I want to figure out where my graph is associated with the x-axis. Here's another x-axis. Here I got a big gap until I get another x order pair. And then it would be this one, and then this one, and then another hole, and then another x value, and then the infinity. So this first one would be negative infinity. Then this one right here is -3. Then I got a gap. Then this one starts up again at 0, and it goes to 2, picks up again at 3, and then infinity. So just to show you, we're only talking x here. So now let's write that in interval notation. So for this little piece of the graph, it's going to go from negative infinity up to -3. It was an open circle on the -3, so I'm going to put a parentheses around it. Now where there's no x, where I just did this, all this yellow, I'm going to union that with my next starting point, which is the 0, and it was a closed circle, so it gets a bracket. It goes up to the next number, which is 2, with a bracket, it's closed. Union that with the next closed circle, which is on 3, and then it goes to infinity. Yes?
If it's the arrow's going down, why isn't the infinity in the y, not the x?
Okay, so yeah, the arrow looks like it's pointing down, but really I guess it should look more like it's pointing down into the side. So really what this means is it's probably just inching a little bit to the side, but maybe going down faster. So eventually this arrow means it's going to keep going this way too, which will eventually cover infinity along the x.
Won't it also cover it along the y?
Yeah, we're going to do the y next for the range. So right now we're only talking x's.
Oh.
Good? Okay, so now we're going to do that, and yes, we're going to get a negative infinity for the y. Okay, let's try the range now. All right, so for the range, let me see if I can. Okay, so now for the range is the y. We're going to go from bottom to top. So notice as I'm walking up this way, the first thing I encounter is the arrow. So that would be the negative infinity. And now if I keep walking up, the next place I hit that's got a point is this open circle here. But if you look over here to the right, this closed circle over here takes over and it keeps on going. So we don't put a stopping point yet. This is where we finally stop at the +2 with a bracket because it was a closed circle. Then I've got a little bit of a gap, and then it starts up again right here at the +3. So union, +3, and now going to infinity. My graph, again from left to right, this one's going up, it's increasing. This one's going up, it's increasing. And this one's also rising from left to right. So the whole graph is increasing. So all I'm going to do is retake this whole domain, rewrite it under my increasing category here, but change all the brackets to parentheses. I do not have any decreasing or constant. So I'm just going to take negative infinity, -3, union 0, 2, union 3, infinity. So rewrite everything, just take out the brackets. Because this entire graph, all 3 pieces of it, is all increasing. So it's increasing over the entire domain. Try another one. So again, this one, again, if you're coming across, so again, remember domain is x. So as I'm coming across, the first thing I'm going to hit is negative infinity. Then you can see that it's going to hit this point here. This is where it stops. after from the negative infinity. So that's going to be -3. And it's a closed circle, so it's a bracket. I've got my little gap here. So then it picks back up again at -2. And then it continues on here. And then it hits 0. Closed circle. Another little gap here. And I'm just going to say this point's on 1. And it's an open circle. So I'm going to union that with a parenthesis and then 1 to infinity. Now for the range, bottom to top. So the first thing I encounter in the range as I'm going up is the negative infinity, the arrow. Then it stops here at -3. It's an open circle, so I'm going to put a parentheses. Then I've got my little gap here, and then it picks back up again at -2. And it continues until 0. Another little gap. And it picks back up at +2 to infinity. So again, notice this line is falling from left to right. So this is decreasing. This one's decreasing, and so is this one. So again, it's decreasing over the entire domain. So again, I can just rewrite the domain. There's no increasing, but the decreasing gets the whole domain again, but use all parentheses. And the constant doesn't apply. Yes. I'm going to add a slide so you can see a constant function. So let me make a coordinate plane here. So let's say our graph all right, so let's just do this little one. So we can see here that over here is the negative infinity. So from negative infinity up to -3. Actually, it's going to be continuous. Let's see. Let's do this. This is going to be all real numbers. So let me do this different. So my domain here, let's just do it piece by piece. So domain is going to be all real numbers, because eventually these arrows are going to cover everything. The range, however, the highest point it gets is going to be here at the 2. So it's going to be from bottom to top. So it would be from negative infinity up to the 2. Now, for the increasing, decreasing, and constant, so for the increasing, you can see that it's going to increase from negative infinity up to the -3 with only parentheses. And that's the only place that it increases, okay? So I'm pulling out of the all real numbers just that piece of it. Then for the constant part, it's going to go from -3 up to the 0 where it stops being constant. And then for the decreasing, it picks back up at 0 to infinity. So for the, let's see, so for the increasing part, it was just this. For the constant part, it's just this little piece. And then for the decreasing part, it would be over here. And again, always use parentheses and not brackets. So those are all parentheses there. Good? So that's how you could do it if it's got all three different things going on. And I'm going to do more examples of this part tomorrow where it'll be different things. All right, next is the function notation. All right, so this function notation is just a fancy way of saying y equals. So you've been used to seeing equations that have like y equals x plus 1. Now they're introducing, instead of saying y equals, they're going to say f of x equals x plus 1. So a fancy way of saying y equals, or the dependent variable y. So what will happen is they're going to give you your independent variable or your input in a parentheses. So like for example, if I said find f of 2, given this function, what this means is every place that I see x, I'm going to replace it with 2, and then I can find the value of f of 2, and that would be 3. So let's try another example where it's more complicated. So here is my function, and again, all I'm doing is replacing each one of these x's with the number 2. And then once I plug it in, I'm following order of operations to simplify it. So I would plug in 2 and square it. 5 times 2, 2 squared, 10. And then now I'm going to just add these up left to right. And I would get positive 6 minus 3 and get f of 2 is equal to 3. And what this is like you could do your function table, maybe that you did in Algebra 1, where they gave you inputs. You were given maybe the equation here in the middle. And then they gave you various numbers to plug in to get your y's, which then created ordered pairs. So this is just a fancy way of doing a function table. Whenever I replace the value of a variable, I always take whatever that value is and I put it in parentheses. Because if I were to put that negative sign in there, it would change my answer. So that negative sign stays outside, and then I only square the 2, and then the negative sign goes in front. So whenever you put in a negative number and you square it, that would make it positive. But in this case, the negative was already there. So whenever I replace a variable with a value, I always put it in a parentheses. All right, so let's try plugging in f of 0. So again, just plug it in. Like if I did it in my table here, I would do negative 0 squared plus 5 times 0 minus 3, 0 plus 0 minus 3, and I get negative 3. If you were looking to get order pairs, this one became the order pair 2, 3. This would be the order pair 0, negative 3. So it's just another way, instead of doing a whole function table, you can just do it by plugging in. Now, they may also ask you to replace x with a variable and not a number. So negative x squared plus 5x minus 3. Replace x with q. And there's your simplified answer. That's all you do. We're not trying to factor anything. We're just replacing it and simplifying. Let's try 2 more examples. Again, I'm going to take out x and put in place of it a plus 1. So g of a plus 1 is equal to 2 times a plus 1 plus 3. Distribute. I get 2a plus 2. Drop down the plus 3. Group these, and you're done. So g of a plus 1 is equal to 2a plus 5.
We have to keep the A+1.
If they just ask you to write it like this and show what it equals, you can just show that. If it asks you to write it as a coordinate, you would write it as a plus 1, comma, 2a plus 5. Okay, because this is, again, what you're plugging in for x. This answer you're getting is really like your y. Over here, we're going to plug in x plus 1. Again, when I plug it in, I'm putting it in parentheses. And now I got to FOIL this thing. So really what you're doing is x plus 1 times x plus 1. And you get x squared plus 2x plus 1. Distribute the negative 3. And now go back and combine like terms. I can combine the 2x and the negative 3x. So the x squared stays. This becomes negative x. This becomes 1 minus 3 plus 1, which is negative 1. So h of x plus 1 is equal to x squared minus x minus 1. And when you write this function notation, they may change it up and use a different letter every time. Their common one that they like to use for functions is f of x. But you might see g of x, h of x, k of x, any letter that they want to use, especially if you have more than one function happening in your problem. Homework that's due Friday, it's broken up. This is the simple stuff. Should be easy. You should be able to do it really quickly. This last part are the graphs. So if you want to attempt them tonight, I will also do more examples of the graphs tomorrow in class. But this homework again is due Friday. We have a quiz on this on Tuesday and on 2-3. So on 2 lessons. That is it.